We're going to get started in 1 minute. Okay, good afternoon. Looks like we're gonna have a couple of students in the classroom today, and then the rest of you in the online hybrid session. That's fine. Just remember that for the exam, you have to come up to the class. So we're gonna have our first exam when we get closer to the spring break in March. So if you need to start making plans for being in the classroom for that time of the semester. And then on our previous lecture, we were focusing on the modeling aspects of this class, modeling analysis manufacturing systems. So we completed that lab exercise, and now you have the assignment in which you are using the sequence of seize, delay, release, not only to model a machine, but also to represent the steps associated with an operator setting up the machines and also doing the removal of parts. Today we're going to go back to our theoretical aspect of the class, in which we are studying models, mathematical models to describe the operation of these manufacturing systems. And in our last lecture on this topic, we started discussing the variability basics and how that impacts the performance and how we study these manufacturing systems. So just a quick recap. These are the topics that we started discussing, and today we're going to focus on that flow variability aspect. So we introduced the variability aspect and how that was different between randomness. What are the things that we can control? How can we use our probability intuition? What is variability? And what are sources of variability? And how to analyze variability in terms of quantifiable means. So we defined these parameters, and actually we had a big list of different parameters that you started learning a week ago. We also classify the type of variability based on the coefficient of variation. So if it is less than 0.75, it was considered low variability. Between 0.75 and 1.33, the moderate variability, and then over 1.33, high variability. We discussed this example. We concluded that we needed a way to consider variability that also take into account these outliers, like 500 in the third machine, because if we don't do that, then we can get the wrong feedback from the analysis. And so how do we consider these rare events properties? And we studied the causes of variability, how to model those. We go through this example between comparison of these two machines. And we also discussed the non-preemptive outages, how we can model those. And we went through this example. And I think after this one, that was the last thing we did. This is the summary of the equations that we studied last time. And then that's where we stop. So today we're gonna start from this point. We're gonna discuss variability from the flow point of view, flow in terms of the entities going through the facility and going through the manufacturing line. So to illustrate the flow variability, variability at one station can affect the behavior of other stations in a line by means of another type of variability, which we call flow variability. So what we are saying is this has an impact, okay? And it's going to affect, if you are not managing variability properly, you can see that variability that is creating problems into your process can be extended to other areas of the process as well. So variability at one station can affect the behavior of other stations in line by means of another type of variability, which is what we call flow variability. And then I'm illustrating what I mean by low variability and high variability in this slide. You can see at the top of this figure, low variability shows entities arriving into the system and they're spread out. Essentially, they're arriving more or less, the inter-arrival times are about the same. So you have an arrival, they have some time in between, then another arrival, some time in between, another arrival, and so on. So an arrival will be represented by these dots. So arrival, some space in between, then another arrival. But you see that even though the inter-arrival time is not the same, they follow a space in between. And then when we look at the high variability arrivals, you have several entities arriving at the same time, and then you have a space with no arrivals, then a couple come in, some space without arrivals, then a group of them arriving, and then a long space in between, and then another arrival. So the spread is not balanced. You have a group arriving at some point, and then another group, and then another group. So this is the difference between low variability and high variability. It's not that you're going to get more or less. It's how they are arriving into the system. Are they arriving at the same pace? or more or less at the same pace, or they have different groups arriving at different times. So high variability at the bottom, low variability at the top. You see here, you have these entities arriving more or less same arrival time, smooth. And then you have here one item arriving and then a group, and then some time in between, and then another group, and some time in between, and then another group. So this is bursty. There's no smooth arrival pattern. You get a group arriving at different time periods. So how do we measure this flow variability? Now we are going to be looking at the time between arrivals, interarrival times. If you remember from the models that we've been building in ARENA, they ask for the interarrival times, meaning that time in between two arrivals. That's what's going to be defining this interarrival time. So you can have multiple arrivals and you're going to be measuring the time in between. That's the interarrival time. Okay, and that's going to be modeled with this TA, mean time in between arrivals. Then the arrival rate is going to be 1 over that. Okay, so so if you have, let's say 10 minutes, this is 10 minutes per arrival, interarrival time. Every 10 minutes, you get an arrival. If you do 1 over that, you get 1/10 of an arrival per minute. Okay, so the arrival rate is basically the 1 over that mean interarrival time. And then the standard deviation is measuring that variability, and then we have the coefficient of variation that is using that sigma A divided by the mean between arrivals. So in order for the workstation to keep up with the arrivals, we need to have an RE or a bottleneck rate, an efficient bottleneck rate that is greater than this arrival rate. Okay, so in order for the workstation to keep up with the arrivals, RE needs to be greater than this RA. So for the propagation of variability, I have here an example that is trying to illustrate how this is spread out through the line. Yes. So what that's stating is that the processing time is greater than the arrival rate, or that bottleneck rate is greater than the arrival rate. So if you're receiving 1/10 of an arrival per minute, you need to make sure that you have enough, your processing time is fast enough to accommodate those arrivals that are coming into your system. If it is too slow, then you know that you're going to be creating a queue for your system. Yes. So propagation of variability, you're looking at single machine station here and multi-machine station at the bottom. So what we are illustrating here is, should we just go back to our definition. Okay. I apologize for, I thought I had a slide with with all the parameters, but that's not the case. So, okay, let's go back to. So we are looking at the propagation of this coefficient of variation at a single machine station right here. And then you see that there's a coefficient of variation that is going to be associated with the arrival of the entities, and then there's a coefficient of variation that is associated with the station itself. And the combination of the two will provide a different coefficient of variation, which we're going to call the departure, or the coefficient of variation of the square coefficient of variation of the departure. And that's what's going to become this new CA square of the next station. Okay, so the combination of these two will create this departure coefficient of variation, square coefficient of variation, which is going to be equal to the arrival coefficient of variation for the next station. And if we have another station, then the combination of that coefficient of variation plus the one for the station is going to generate a new one. And that's, so the variability here is being propagated. You're taking that variability associated with the arrival, you're combining that with the process that is happening in station I, you're creating a new coefficient of variation, and that's being propagated to the next station in the system. So for a single machine station, this CD, or this square coefficient of variation for the departure, is going to be given by this expression right here, U squared times the coefficient of variation for that station, effective coefficient of variation for the station, plus 1 minus U squared times the coefficient of square coefficient of variation of the arrival. Remember that I use the utilization for the station, and that could be computed based on the RA times TE. So the departure variability, or that CD, the square CD, depends on the arrival variability and the process variability, the combination of the two. And this is how we compute that. For a multi-machine station, let's say you have 2, 3, 4, 5 machines, we can compute that C squared of the departure by using this expression, where M is equal to the number of machines in the number of identical machines. And the utilization is given by this expression. So 2 ways of computing this propagation of variability, 2 ways of computing this CD, or square coefficient of variation for the departure process. It will depend on the type of manufacturing line that you're studying. For a single machine, you use the expression at the top. For multi-machines, you use the expression at the bottom. But the idea with these equations is that you can see how variability can be propagated and how the variability occurring at each station is going to have an impact on the next one. So if we have a very high coefficient of variation in the arrival process, just in the arrival process, you know that that variability is going to be propagated across the system because it's connected to what you're going to see as your departure coefficient of variation. It's going to impact that value. Mathematically, we can see it. So let's look at the propagation of variability for high utilization station. So we have a basically what these pictures are trying to illustrate is what would be the impact of having a low variability in the arrival process and a high variability in the process itself. So we have that combination. What we are going to observe as an output is a high variability. combination of both high variability in the arrivals and in the process will also give you a high variability in the departure. Low variability and low variability, this is what we expect, right? To have a low variability in the departure process. And the last one is not the one that is intuitive, but if you have high variability in the arrival process and a low variability in the process itself, then the result will have also a low variability. So basically what this is saying is your final variability or departure variability is mostly impacted by the variability that you're observing in the process. This can somehow control this, but the opposite is not right. It's not the same. Okay, so high variability in the arrivals, low variability in the processing station provides you with a coefficient of variation that is low variability for the departure process. So in conclusion, for variability out of a high utilization station is determined primarily by the process variability at the station. Let's see what happens for a low utilization station. Low variability, high variability. If you have low utilization, meaning that you have more than enough capacity here, then you should be able to accommodate that into your system. So it gives you low variability. High variability and high variability in the process is also conducting to high variability in the departure process. Low variability and low variability gives you low variability. And high variability with low variability, in this case, is also providing you with a high variability departure process. So for low variability, the flow variability out of a low utilization station is determined primarily by the flow variability into that station. Which is the opposite of what we observe with the high variability. I'm sorry, with a high utilization station. So going back here, see high variability, low variability gives you a low variability. For a low utilization station, we get high variability, low variability. Since this is low utilization, you have more than enough capacity to take into to process all these entities, and you're going to be processing them as they arrive. Right? Every time they arrive, there's no queue. They're going to go in and they're going to go out. So you're not going to have that space, say that the machine is not going to help you control the output of the process, because since there's no queue, they're basically going in and going out. You have more than enough capacity, you have low utilization, there's no waiting for these parts. So if they arrive with high variability, they are going to depart with a high variability. In this case, since you have a high utilization station, meaning that that machine is busy most of the time, it doesn't matter if these parts are arriving with this high variability, because they're going at the end, they're going to have to come up with arrive to this queue, and they're going to have to wait. This machine is busy, and the machine is going to be processing based on the pace that the machine has. The queue is going to be holding the variability, and then they're going to be going out based on the process that is based on the machine processing time. So that's the difference. High utilization, you get to see all these queues, right? You see these queues forming here. because the machines are busy. So they're going, I mean, even though they have high variability, they're arriving to this queue. And the queue is going to put a buffer. Okay, even though you are coming in this way, you have to wait until the machine becomes available. That's not the case here. There's no queue. They'll come in, they will very low utilization. Don't wait. So they're going to go out. As they come in, they come out. So what you're going to be observing is, if I come with low variability, I leave with low variability. If I come with high variability, I'm going to leave with high variability. And you see this mimics this. This mimics this, this mimics this, this mimics this, because there's no waiting. So high variability end up with high variability, low variability with low variability, high variability with high variability. Doesn't matter what type of variability you have here. In the previous one, pattern, you see this pattern is different here. Pattern, different. Well, they're the same. These two are the same. And these are different. So in conclusion, for low utilization, the flow variability out of a low utilization station is determined primarily by the flow variability into that station. Okay, so two different scenarios, two different outcomes. One is depending on the process, the other one is depending on the arrivals. So propagation of variability, one more time, here are the equations. We're going to compute this square coefficient of variation square using this equation for a single machine, and the square coefficient of variation for the departure for multiple machine stations using this equation. So what are the basic variability takeaways from this lecture? For variability measures, we have the coefficient of variation of effective process time. So that's CE. And we have the coefficient of variation of the interarrival times, CA. What are the components of process variability? We have the failures, the setups, and many others. Deflate capacity and inflate variability. Long infrequent disruptions, worse than short frequent ones, and we saw that with the example. And what are the consequences of variability? They cause congestion. It propagates, as we saw in the examples. Variability and utilization both interact. And we're going to talk about this on the next lecture. Pool variability is less destructive than individual variability. And that's the last part of this first part of lecture 2. So we are going to continue our discussion with the next group of slides, which is part 2 of variability basics. And today we're gonna, in this lecture, we are also gonna study the queuing models and how they interact with what we are trying to achieve in terms of modeling manufacturing systems. So we're gonna look at the queuing notation and measures, the fundamental relations, the MM1 queue, performance measures, systems with general process and interarrival times, parallel machines, and parallel machines and general times. And we're going to talk about the effects of blocking. So are you guys familiar with queuing models? Have you heard about queuing models before? Okay, how about you, Saha? Should be familiar, you're industrial engineer. So we now turn to the problem of evaluating the impact of variability on performance measures for a line. And as you're seeing, you're going to be focusing on the working process, the cycle time, and the throughput. The actual process time typically represent only a small fraction, 5 to 10% of the total cycle time. So if you think about any system, like if you go for a restaurant or if you go to, I don't know, a bank, the time that you actually spend getting service is very small, whereas the time that you actually spend in the system is typically high. So you spend most of the time doing in a queue, or you spend it in other things. Maybe if you're in the post office, you're preparing a package, then you have to do the queue, but the actual time that you spend with the server is very short. And that's what we are trying to say. So typically, process time, same thing for a manufacturing line. Parts are going to be waiting in the warehouse. They're going to be moved to the manufacturing floor. They're going to be stocked. They're going to be put into the line. And then the actual time that they spend in the processing is very small. The majority of the extra time is spent waiting for various resources. So we need to understand the underlying causes of all this waiting. So again, we call it queuing theory to the science of waiting. So we can do just a class on queuing models. Okay, we can spend a semester talking about queuing models, queuing theory. That by itself, there are books that are being written only on that. For the purpose of this class, we're going to be focusing on the impact on variability in manufacturing systems. So the importance of queuing, manufacturing plants are queuing networks. We can model them as queuing networks, in which you have products moving, let's say in a manufacturing line, they wait in a queue, they're processed, they have another queue, they're processed, and so on. And queuing and waiting time comprise the majority of the cycle time. So what are some of the system characteristics? We have the arrival process, the service process. We are also looking at the capacity of each station, the number of servers, the maximum queue size. So in one of the labs, we were putting a capacity, and then we were counting the ones that were not able to stay in the queue. The service discipline. So we're going to use first come, first serve, last come, first serve, early departure date, shortest processing time. So all those are disciplines. So FC, first come, first serve. Let's go. Early departure. SPT is shortest crossing time. So your queue can be organized in such a way that you are gonna take care of the first item arriving into the queue, or you wanna take care of the last item first, or you wanna take care of the product that has the earliest departure date, meaning that you have to deliver this as soon as possible. So you wanna put that first. Or the shortest processing time. So out of all the products that you have in line, you want to take care of the one that takes the less amount of time. So those are policies or disciplines for the queues that you can use. If you look at the arena, If you look at the Q modules, you'll see that these disciplines are listed there. You can select between first come, first serve. You can select between early departure date and so on. We have bulking, routing, and many more. So let's define some of the notation and measures that are used in queuing. So to use queuing theory to describe the performance of a single workstation, we'll assume that we know the following parameters. RA is the arrivals, rate of arrivals in just per unit time to station, in a serial line without yield loss or rework. RA is equal to the throughput at every workstation. TA is the average time between arrivals and is the same as 1 over RA. CAR is the coefficient of variation for the arrival process. M is the number of parallel machines at the station. B if the buffer size, so for example, maximum number of jobs allowed in the system. TE is the mean effective processing time. The rate or the capacity of the workstation is given by RE equals M divided by TE, and CE is the coefficient of variation of the effective processing time. So we are going to assume that we know these parameters. And the performance measures will focus on the probability there are n jobs at a station, CTQ, which is the expected waiting time spent in the queue. So let me do something. So when I put those here, so we remember those. Cycle time is going to be equal to CTQ plus TE. CTQ is the cycle time in the queue, and TE is the effective processing time. Working process, WIP equals RA. RA is the arrival rate times cycle time, which is this cycle time. And working process in the queue equals RA times CTQ. So basically what we're saying is we have a server here. We have a queue. Right, so CT is looking, this is point A, and this is point B. So CT is looking at A up to B. CTQ over C will go from A to C. And WIP is going to go also from A to C. And then the utilization is given here by RA divided by RE, which is equal to RA times TE divided by M. So as the result, we have the following. If we know CTQ, we can compute WIP WIPQ and the cycle time. So you can work backwards, or you can use these equations. If you know the cycle time in the queue, you can find the rest of them. So here's the Kendall's classification for a queue. We have a server, a queue, and then we have three letters A, B, C. A is representing the arrival process, B is the service process, and C is the number of machines. So we use this notation right here. Formation is presented in that sequence. A will go first. So the information that is placed in A, in the location of A, is always referring to the arrival process. The information that is presented next in the space where B is the service process. And then C is in third place, represents the number of machines. For the classification scheme, we also have some notation. Like for example, M corresponds to the exponential Markovian distribution. G represents the completely general distribution, and D represents constant or deterministic distribution. So for example, if I write something like this is saying that my arrival process follows an exponential distribution. The service process also follows an exponential distribution, and that my server has only one machine. Okay, so MM1. And that's the system that we're going to study next. So the MM1Q. This is one of the most simple systems. So one of the simplest queuing systems to analyze. It assumes exponential interarrival times, a single machine with exponential process times, a first come first served protocol, and unlimited space for jobs waiting in queue. The MM1 queue is good because in theory, it is tractable, meaning that we can solve mathematically to find the optimal solution, and but offers valuable insight into more complex and realistic systems. So for the MM1Q, we have the following equations. The working process equals the utilization divided by 1 minus the utilization. Cycle time will be equal to WIP divided by the arrival rate. And if you solve that equation, you'll find that this is equal to TE divided by 1 minus U. Average cycle time in Q, CTQ, is going to be equal to CT for MM1 minus TE, which if you solve for that, you will get U divided by 1 minus UTE. And then the average WIP, or working process, WIPQ equals RA times CTQ, which is going to be equal to U squared divided by 1 minus U. Yeah. What is what? Oh, so MM1 is the type of queue system. Yes, so this is saying that this arrival process follows an exponential distribution because it's A. B is for the service process time, also follows an exponential. And C is the number of machines, so we have only one machine. Okay, so we are defining the equations for an MM1 system. this, and why are we focusing on this one? Because this one is tractable, meaning that we can come up with these mathematical expressions that will give us the optimal solution. But for other systems, that's not the case. If we look at other type of distributions, like let's say instead of following an exponential, it follows a gamma distribution, the processing times and the arrival times, we are not able to get those expressions for under those circumstances. But we focus on this one because it provides some good insights on the rest of the systems. So let's look at this example. Recall that in the Breyer patch manufacturing example, the arrival rate to the tortuous was 2000 was 2.87 joules per hour. So that's the arrival rate. Assume now that times between arrivals are exponentially distributed, which is not a bad assumption if jobs are arriving from many different locations. Also recall that the production rate is 3 jobs per hour. So TE is equal to 1/3, and that C, which is the coefficient of variation, for the effective processing time equals 1. Since the effective process time have a coefficient of variation of 1, just as the exponential distribution does, it is reasonable to use the MM1 model to represent this machine. So we can compute the parameters for this system using the equations that we just defined here. So the utilization we're going to need the utilization. You see most of the equations use the utilization. So we have to compute the utilization here. So if you remember from, let me go back to slide 8, utilization. We can compute the utilization using that equation, RA divided by RE, or RA times TE divided by M. And we know that RE equals M divided by TE. So let's put that in here. U equals RA divided by RE, and RE is equal to M divided by TE. So M is the number of machines. TE is 1/3. So that means that RE equals 1/1/3. So RE equals 3. Then the utilization equals 2.8075 divided by 3. So this is equal to 0.9583. Okay, so you got that. So now using the rest, we can compute the working process. Equals U divided by 1 minus U. So we have the utilization here. So the working process is 23 jobs. Cycle time equals the working process divided by the throughput. So the working process is 23, and the throughput. So in this case, where is it? What will be the throughput? Let's see if I find that description here. So the throughput in MM1 systems is equal to the arrival rate. Okay, so our arrival rate in this case is 2.875. And that will be equals to 8 hours. CTQ equals cycle time minus TE. So our cycle time is 8 hours. TE in hours is 1/3, 0.333. So this is 7.6667 hours. And then W Q equals throughput times CTQ, which is 2.8075 times 7.6667, and this is 22.04, 17 jumps. So those working process in the queue are quite high. We see that the WIP and the cycle time are much smaller than those for the Air X19 under the certain demand conditions. However, to model the non-exponential Air X19, we need a more general model than the MM1. So 22.0417 jobs in the queue, typically in a cycle time of about 8 hours. So we're talking about a long process here for this jobs. So let's talk about the systems with general process times and interruptible times. So the exponential has a property that is called the memoryless property. Any of you remember what that property is all about? So the exponential from this perspective, we are using it to model the processing times and the arrival times, interarrival times. So the memoryless property of the exponential distribution, what it said is, doesn't matter what happens before this event, is not going to impact what's going to happen next. Okay, so if I got arrivals 10 minutes ago, 15 minutes ago, 20 minutes ago, doesn't matter what happens, that's not going to impact my next arrival. So that's the memoryless property. Without the memoryless property of the exponential to facilitate the analysis, we cannot compute the exact performance measures for GG1 systems. So GG1 queues, we go back here, they're representing our systems with general processes, processing and interarrival time. We go back here. a completely general distribution, and we are assuming now to have a GG1 system. So it's no longer an exponential distribution. These are completely general. They don't fit a specific probability model. General, completely general distribution. So without the memoryless property of the exponential to facilitate the analysis, we cannot compute exact performance measures for these type of systems. We can estimate them by means of a two-moment approximation, which makes use of only the mean and standard deviation. Or the coefficient of variation of the interarrival and processing or process time distributions. As we did for the MM1 case, we will proceed by first developing an expression for the waiting queue and then computing the other performance measures. Okay, so we are gonna do that. So for the CDQ, for a GG1 or general process, general arrival time system, we have an expression that considers the variability, the utilization, and the time, the processing time. And then that's the expression. We have variability, utilization, and the process time. Okay, so this will be B, this will be U, and this is gonna be T. So this VUT equation has a formula considering the variability, and you can see that it takes into account the variability of the arrival and also the variability of the processing time. So it has the square coefficient of variation of both, the summation of the two divided by 2. So it's like averaging those two coefficients. And then the utilization is just the utilization of the station, and then T is just the processing time. So this model is a useful model of single machine workstations. It separates terms for variability, utilization, and processing time. And CDQ and other measures increase with these two coefficients. So if we increase the variability for the arrival process or the processing time, you know that the entire queue or cycle time for the queue is going to increase. Flow variability, process variability, and both can combine to inflate the queue time. And separate into three terms. This expression has a dimensionless variability term. V, a utilization term, U, and a time term, T. And as you can see, the expression is clearly showing that this variability causes congestion. So the highest the variability, the highest is going to be your cycle time in the queue. So let's look at this example again. and consider the here X19. Recall that this machine has a high variability. Square coefficient of variability for the processing time was 6.25. Again, assume the time between job arrivals is exponential. That is CA equals, or square coefficient of variation equals 1. And the utilization of the here X19 is 0.95. Hence, we can use the VUT equation to compute the expected Q time as follows. CDQ will be equal to CA square, CE square divided by 2 times U divided by 1 minus U times TE. In this case, we have 1 for the square coefficient of variation plus 6.25 for CE square divided by 2. And then the utilization 0.9583, 1 minus 0.9583, and all that multiplied by TE, which in this case was 20. So this is equal to 1,667.5 minutes, which is equal to 27.79 hours. Now, suppose that the here X19 fits the tortuous 2000. So this is coming from our previous example, lecture 2, part 1. Yeah, so we have the TE for that machine there. Good question. So now suppose that this X19 feeds the tortuous 2000. There's no yield loss, so the rate into the tortuous 2000 is the same as that into the X19. And hence, since the two machines have the same effective rate, they will have the same utilization. However, to use the VUT equation, we must find the arrival coefficient of variation, CA, to the tortuous 2000. We do this by finding the departure coefficient of variation from the here X19. So we have to find CD by using the linking equation A pointing, which is given in lecture 2, part 1, slide 40. In that equation, that's the one that we discussed at the beginning of the lecture, is the following. The C coefficient of variation of the departure equals CE square times U square plus CA square times 1 minus U square. Okay, so if I show you, let me show you that. In case you don't remember. This is the expression that I'm referring to. Okay, so CD coefficient of variation of the departure. So now we're saying that the tortuous and the X19 are like this. So now I need to compute this square coefficient of variation for the departure process in order to know CA square of T. Okay, because CD square equals, yes, like we're seeing here. So let's go back here. So using this information, we have CE square is 6.25 times the utilization square, 0.95, 83 square plus 1.0, 1 minus 0.95, 83 square. And then this is gonna be equal to 5.8216. And now we can compute the CTQ. Okay, so let's do that. CTQ equals CA square plus CE square divided by 2 times U 1 minus U. So now we are gonna use this CD square is gonna be equal to our CA square. And we are gonna substitute that into here. In this equation? In the other set of slides? Oh, so this I? This I? It is representing the machine. So I is the identifier. This is for machine one. It is not this. It's not representing a number in the process. It's just identifying. Yeah. Good question. So here. So now we can compute the CT square. CTQ, I'm sorry, CTQ will be equal to 5.82 plus 1.0 squared divided by 2, 0.95, 83, 1 minus 0.95, 83 times 20, and this is 1,568.97 minutes. Equals 26.15 hours. So these two numbers are not very different. So notice that the Q time at the $2,000 is almost as large as that for the hair X19. Even though the X19 has much higher process variability. The excess time and congestion is a consequence of the propagation of variability. From the upstream here X19. So remember we have the X19 and then we have the tortuous. This X19 is feeding this tortuous machine. And remember that X19 has very high variability. The square coefficient of variation, the CE, was 6.25. So it has higher variability than the tortuous, right? But we are seeing that the high variability is being now transferred into this tortuous machine because of the consequence of the propagation of variability to the manufacturing line. So if you have a very high variability at the beginning of your process, you should expect that to spread out into the rest of the process. So if we can conclude something about this is if you have no option but to have some type of variability in your manufacturing process, you don't want that to happen at the beginning. You want to put that as farther as possible into the process, let's say the last few stations, because in that way you're going to limit the propagation of the variability through the manufacturing line. So here's the same formula, but this is for the case in which you have more than one machine in the station. So the analysis that we are making is based on single machines, right? But if you have multiple machines, parallel machines into each station, then you have to use this formula that is in this slide that considers the number of machines that you have in the station. This is a useful model of multi-machine workstations. It's extremely general, fast and accurate, and easily implemented in the spreadsheet. So we're going to stop here. And then in our next lecture, we're going to talk about the effects of blocking. Any questions? Okay. So, yes. Any questions from the people in the virtual environment?
That's good. Everything looks good. Thank you.
So I'm going to stop the video now. And then I'll see you guys again on Monday.
Yeah, have a good weekend. Thank you so much.